Cool. So that's it. You can do that exploration. You can do that for all the five of the big five. It's a very fun exercise. Recommend that you do. Now, let's talk about the gold of what SMCR is covering. SMCR is covering sampling distributions. You guys are going to hear this term all the time. And you're like probably reading the book and you're reading the book and it says, oh yeah, so this is sampling distributions do this, sampling distributions do that. And it's like you're reading a book when you're reading a novel that has a word that you don't know and you just like follow along and you try to see if that makes sense. Well, that shit doesn't work here. Okay. You're not going to find out that, the definition of an attic, if you don't know the word attic, just by seeing that it's on top of the house. No, it's not self-explanatory. This is very, very complex. So you have to understand the meaning of sampling distributions. That's what we're going to do right now. This is the most important word that you need to know in order to understand SMCR. So let's get to it, okay? So remember that we live in a simulation. Normal distributions can be reverse engineered. So we can also reverse engineer the shape of data distributions. How? How do we do that? Well, let's go back to the height example. Let's find the average height of the Dutch. Okay, how do we do that? So first we're going to start from a sample statistic. Okay, sample statistic is literally whatever number you can get from a sample. Okay, I know that this sounds weird. This sounds like, what the fuck are you saying, man? For now, let's assume that sample statistic can be an average, can be an example of a sample statistic. So let's say that we're trying to find the average height of Dutch people. Statistic, by the way, means number, okay? So we can also call this the sample number, like literally any number from a sample, okay? So whenever I see sample statistic, I want you to think of sample number, okay? So the sample number that we're focusing on, the number that's coming from the sample, is the average, okay? And the sample is about the height of Dutch people, so it's average height of Dutch people. Cool. So we start from this point, which is the population distribution, right? The population distribution of height in the Netherlands respects a normal distribution. Very important. We're only interested in the average of the Dutch population. We're not trying to find out what this distribution is. Okay, that's for like a different type of study, different type of statistics, not inferential statistics. When you're dealing with a average of the sample statistic, which is something that we do quite a lot. Okay, so let's say that right now we are Jesus himself, and we know everything. And one of the things that we know is the average height of the Dutch population. That is, if you were to go and ask every single one of those 17 million people and divide that by 17 million, let's say hypothetically that number would be 179. Okay, that's the population parameter, right? You can replace the word parameter by number or by statistic. You could say the population number. Okay, so it's the number that's the real number, the real average of the population. Cool. What do we do with that? We get one sample. Let's say we randomly select 1,000 people, 1,000 Dutch people, to, for our sample. This is one sample, and we get the average height within that sample. And let's say that the average height within this sample is 180 instead of 179. So it means that we have one too many tall people in our sample, which is pulling our average, 1 centimeter up. Great. That's pretty still accurate. This number is what we call the sample statistic, right? This is the number within the sample, okay? 180. Cool. So let's differentiate between population parameter and sample statistic. Cool. Well, it so happens that if you're drawing a sample from a population, if you're drawing a sample from a population, you're going to have a normal distribution as well, right, of height. So people in your sample, they're going to be, the vast majority are going to have an average height. So only a few people are going to be too tall. Only a few people are going to be too short, quite like the population. That's what it means to be representative of the population. So let's say you have a comparison. You can use this distribution for comparison height within the sample, right? You can't really use this for comparison and height within the population for all reasons that we don't have to discuss. But, just keep in mind that this distribution at the bottom allows you to make comparisons in height within the sample. The distribution at the top allows us to make comparisons in height within the population. Okay, they're two separate distributions. They should be similar, but they're separate ones. Cool. So let's look at our sample statistic. Our sample statistic is 180. And here, we're also only interested in the average of our sample. Okay, we pretty much ignore everything else about our sample. We only draw our 1,000 people so we can find their average. Cool. So here we have an average of 180. Cool. Now we're building this thing called a sampling distribution. And this is a distribution of all possible averages, okay, in samples. So that is, whenever you draw a sample, what are the chances that you're going to get a height of whatever number? This is abstract. It sucks. Let me show you visually what that is. So ideally, what do we want to do? We're going to take a sample of sample statistics, okay? So what does that mean? Well, we're going to choose a number 25 here. What does that mean? That means we're going to gather 25 samples, okay? So 25 times, we're going to go to the Dutch population. We're going to get 1,000 people randomly selected, get their average, and inform that average over to the sampling distribution. So we have 25 samples. We're going to have 25 averages, right? Because it's going to be 1,000 people times 25. So 1,000 people, 1,000 people, they're total 25,000 people, right? With 25, each of those groups having one particular average. Cool. So here's how we do that. Sample number one, we get 1,000 people, we'll get their average height. Now we got a different average. Wow, are we surprised? No, because every time you draw a new sample, there's random error. So you're going to have a slightly differing average. So now grabbed a new sample, average 178. What do? This is our sample statistic. So we plug that sample statistic into our sampling distribution. Okay, cool. Sample number two, gather a new sample with another 1,000 people. Now they have an average of 177, one too many short people. Cool, no problem. Let's plug that in. The counts, so far we have one sample with 177, one sample with 178. Cool. Let's do it again. Sample number three. Now we had 178 again as the average of sample number three. So we plug that into our distribution. Now we have two samples with average 178. And we keep that keep doing that until we get to sample number 50. When we get to sample number 50, now sample number 50, we had 182, and we plug 182 there. You can see that this sampling distribution is organizing in a shape that's rather familiar. Well, what is that fucking shape? Well, that is what we call a normal distribution. Okay, so because it's a normal distribution, we could just get our contractor, the normal distribution, just place it on top of this data and ignore the data now because we have this drawing as a replacement. And now we see that the most recurring number of samples is 1, 2, 3, 4, 5 samples with average 179. That's great because 179 is also the population parameter, also the real value, the real average in the population. So that's good. You can see that we have all the reason to believe in science because the most recurring samples are going to have a similar value compared to the population, right? Or a value that's pretty close, like 180 or 178. Cool. So 179 here in our sampling distribution is our point estimate because it's the number that we expect a new sample to have, right? It's the average that we expect a new sample to have if we were to just try and bet what the next sample number is going to be, right? And that's true because think about it. If you're really betting on a horse and you see that there's a horse that has the most results, like there's this horse in particular, keeps winning all the time. So, well, let's bet on that fucking horse. That's a great horse to bet on. So the point estimate is the best value you can bet on in terms of what the next sample average is going to be, right? Next sample average being like next time you draw a sample with 1,000 people. Cool. Great. With our sampling distribution, we can also derive a confidence interval for the chances of getting an average of value such. What do I mean by that? So we're 95% confident that when you draw a new sample from the population of 1,000 people, you're going to have a value between 177 and 181 centimeters. You're going to have an average between 177 and 181 centimeters. Remember that we're talking about the average, right? That's the only thing we care about. So that's important because what that's saying pretty much is that in if we were to draw 100 samples of 1,000 people, 95 of those samples would have an average between 177 and 181, pretty much. So important. Here we're mostly interested in this range, right? So I know that we have a point estimate here that's pretty accurate and that's like very seducing to go and find this point estimate. But the important thing here is to know this range, because when we know this range, we know what are the chances that we're going to make an error when we're drawing a sample from the population. Okay, so this is our 95% confidence interval, saying that 95% of the samples between 177 and 181. And if you look at the data that we had before, exactly 95% of the samples have an average between 177 and 181. Also known as 19, if you count, there's 19 samples out of the 25 samples. They had an average between 177 and 181. Only 6 samples out of those 25 had an average outside of this confidence interval, which is great. This is beautiful. I love data. But the problem is that we never actually get the population distribution or this ideal sampling distribution when we're conducting a study. We never know that. So remember when I told you earlier, we got into Jesus mode because now we know everything, right? That's not something that we usually do know. What happens in a study, in a real study, in a real research, paper, is what we call a derived sampling distribution. I'm using this name. The author of SMCR, the teacher, doesn't use this name. That's okay. I'm using this name just to separate the definition between a derived sampling distribution and an ideal sampling distribution, which is the one that we were working with just before. Okay? So this derived sampling distribution is supposed to be a sample of sample statistics as well. But now instead of having 25 averages to compose this distribution, we only have one average. And that's a little problematic. What does that mean? Well, we have a population distribution, which we don't know, right? So we don't know the real value there. We're just like drawing 1,000 people from there, and we're trying to get their average heights and find out what the average height is in the population. Then we get the average height from that sample. And this we know, this we do. So the average here is 178. Okay, cool. We got that average, that's our sample statistic, and we plug that average as the center of this distribution. And this is the time where we have to have faith in statistics. I'm going to assume that the sample statistic that I found, 178, is the point estimate of an ideal sampling distribution. What am I saying? I'm saying that I'm going to believe that this sample is not one of these fucked up exceptions, right? Outside the 95% confidence interval. I'm going to assume that. And that's a pretty flawed assumption, I have to tell you. But it's the best way that we know how to do that. So let me just do the presentation I prepared. So do I know that for a fact? No. But it's, if I have only one sample, it's the best that I can do. And usually, if you're a researcher, you're not going to get funding from the government or whatever funding you're looking for to conduct 25 studies with 1,000 people each. No, you're usually going to get funding for one study with 1,000 people. So you have to work with what we have. So what we have is one simple average. So we're just going to use that average and place it there. So we derive a distribution and confidence interval using theoretical approximation. What do I mean by that? Well, we're just going to pretty much plug 178, and we're going to plug this, we're going to put this distribution on top of this 178, okay? And we're going to say, this is the stretch of this distribution that's appropriate for a sample of 1,000 people. And that holds up because consistently, if you have a sample of 1,000 people and you're going to draw a sampling distribution, ideally, like we just did, the width of that distribution is going to be pretty similar. So you know what the stretch should be for 1,000 people. So you just use the stretch, you place it there, and then based on that, you calculate the lowest and the top range for your 95% confidence interval. Here, it ranges from 176 to 180. But all of that's coming from this sample, okay? So that's great. Just recapping, it should look like something like this. This is the ideal sampling distribution where we have 25 samples, 25 averages of samples put together to build a distribution, right? In this example, we end up having point estimate that's actually very close to the population parameter, right? Well, actually exactly the same as the population parameter. So it should look like that, but it looks like this. It's slightly off 178 compared to 179, but it's pretty close. It's a little off, but actually, in most cases, it's not that bad of an inference. As long as we make sure that we have a representative sample. So that's the faith that we need to have, that the number of participants here is large enough. So 1,000 is pretty large of a number to find an average, and that these participants were randomly selected from the population. If we have these two, we have all the more reason to believe that our derived sampling distribution is somewhat okay, equal to the ideal sampling distribution. So the biggest limitation here is that you assume, based on one single sample statistic, you assume that one single sample statistic to be the population parameter, even though we have no evidence that that's the case. We have some evidence that this should be the case, okay, but we have no evidence that that is the case.